Hi class, today we're going to be talking about the normal distribution continuing in chapter 12 on statistics. The normal distribution is a probability distribution that's symmetric around the mean of the data. We also call this a bell curve that looks like this. So typically we're talking about a normal distribution for a population when we have lots and lots and lots of data points. Things smooth out into a smooth continuous curve where the mean, the median, and the mode all have the same value. And most of the data is grouped here around the mean. So this is like a frequency histogram that we looked at in the earlier sections in chapter 12. Some examples of things that have a normal distribution. Men's heights, for example. Or women's height, but heights, if you think about like all the men in the United States, their heights have a normal distribution. Other things with a normal distribution, IQ, SAT scores. Anything when we're looking at a large population, things that vary slightly among individuals will have a normal distribution. So thinking back from 12.3, the standard deviation tells us how spread out our data in a sample is. The standard deviation is really important with the 68, 95, 99.7 rule and the normal distribution. What this rule tells us when we're looking at a normally distributed population is that 68% of the data is going to fall within one standard deviation above the mean. So here, if we're talking about a sample, X bar is our mean, and S is the standard deviation. So if we go above or below the mean by one standard deviation, 68% of the population, the data from the population, is going to fall in there. Then if we go out to 2 standard deviations, 95% of the data will be captured. And then if we go out to 3 standard deviations, 99.7% of the data will be captured. So there's only 0.3% left over in these little tails here. So what that means is almost everybody in a population or in a large sample from a population is going to be within 3 standard deviations of the mean for any given metric. Let's look at an example. Is that where you can see it? So heights of North American men are normally distributed with a mean of 70 inches and a standard deviation of 4 inches. We want to find the height of a man that is 2 standard deviations above the mean in part A and then 3 standard deviations below the mean. So using the 68, 95, 99.7 rule, I can know what percent of the population is within these standard deviations. So first let's fill in the heights on the bottom associated with being a certain number of standard deviations above or below that mean. So if the standard deviation is 4 inches and the mean is 70, remember we use mu instead of x bar if we're talking about a population mean. One standard deviation above would be 74 inches, then 78, I'm just adding 4, 82, and then going in the other direction below, I'm subtracting 4 away. So 66, 62, 58. Now we can answer the questions. What's the height of an individual that is 2 standard deviations above the mean? 2 standard deviations above the mean is 78 inches. And then 3 standard deviations below the mean be 1, 2, 3, 58 inches. And so thinking about the 68, 95, 99.7 rule, only 0.15% of people are below here in this tail that never really ends. So somebody that is 3 standard deviations below the mean, or 58 inches, would be a very short man in North America. And somebody that is 2 standard deviations above the mean is pretty darn tall, because 95% of men, remember, are in between 62 and 78, in between 2 standard deviations. So looking at questions, similar to what I was just saying, we can ask these sorts of things. What percentage of men have heights in between 66 and 74 inches? So this is 1 standard deviation below the mean and 1 standard deviation above the mean. So in here, straight from the 68, 95, 99.7 rule, I know that 68% of men have heights between 66 and 74 inches, because that's 1 standard deviation below and 1 standard deviation above. Now let's see, what percentage of men have heights between 62 and 70? "62 inches is 2 standard deviations below the mean, and then 70 inches is the mean." So we could think about it this way: 50% of men are below the mean. Now 62 is just 2 standard deviations below the mean. So I'm asking what's happening in between 62 and 70, right? So the rule tells me that 95% of people are in between, or are within 2 standard deviations of the mean. That means 5% would be in these tails to the left and the right, beyond 2 standard deviations away from the mean, which means 2.5% of men are in this tail down here, and similarly 2.5% are in this tail up here, but that's not what we're worried about right now. So if I know that 50% of men are below 70 and then 2.5% of men are below 62, I can subtract 2.5 from 50 until this tells me that 47.5% of men are in between 62 inches and 70 inches. Lastly, I could ask, what about above 78? 78 is 2 standard deviations in the other direction. So answering this question is similar to what we had to do to figure out the part B beforehand. 2.5% of individuals are in the tail that's below 2 standard deviations and above 2 standard deviations. Because the 95 rule tells us that 95% are within 2 standard deviations. So 5% are beyond 2 standard deviations, but that's above and below, so we have to divide it by 2. So above 78 inches, 2.5% of men have heights above 78 inches. So we can ask ourselves kind of naturally where an individual fits in a population given their height. And the z-score tells us how many standard deviations above or below the mean for a population a data item falls. So if we're talking about a sample, remember we use X bar and S for the mean and the standard deviation. And if we are talking about